All right, we're back. We are still on page 12 of notes 2 of Calc C, and we're still talking about what we're now calling Maclaurin polynomials because they're centered at 0. So if a Taylor polynomial is centered at 0, it is now called a Maclaurin polynomial, which I talked about last time isn't my favorite thing. But anyway, when we do this, what you're going to do is you look for, within the function, look for something that you know how to write the polynomial for. So like I see sine of 2x. I know how to write a polynomial for that. So what I'm going to do is start with sine of u. I call this building the polynomial. So I'm going to build it from the ground up. I'm going to start with sine of u, which I have memorized. Sine is an odd function, so it's the odd powers, and it alternates. And there's the factorials, and we're going with 4 non-zero. And I also object to that. I should have just done 3 non-zero, but whatever. And then we wanted, also I'm using x everywhere, so let's go back and erase all those. Cool, cool. U plus dot, dot, dot. So don't worry about this right here, this plus. Even if it was supposed to be a minus, there's a really good chance that I would write plus anyway, because when we get to the general term right here, what we're going to do is we're going to put in a -1 to the n, and that would take care of it, right? If you had written minus there, whatever happens, happens, right? So if you write plus and it's supposed to be minus, it's just going to be plus a negative, and it's going to work out. So basically, I'm just saying don't worry about that. But man, some of you will, and there's like nothing I can do to stop that. But I just tried. All right, this is my 4 non-zero terms. Now what I'm going to do is replace every u that I see with 2x. So like, do you really need to do that step? Oh, I did it again. What the heck? You know what it is? Soon we're going to be doing series, and then it's appropriate for it to be an equal sign. But until then, it is not appropriate. All right, so sine of 2x, approximately 2x minus 2 cubed x cubed over 3 factorial plus 2 to the 5th x to the 5th over 5 factorial minus 2 to the 7th x to the 7th over 7 factorial plus dot, 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 plus -1 to the n. And then here we go. So it's going to be 2. These get, like, they look gross. To the 2n plus 1. X to the 2n plus 1. So I haven't really mentioned this yet. I pretty much will never leave a product or a quotient to a single power. So like, instead of writing the quantity 2x to the 2n plus 1, that's a product raised to a power. I always break it up into like the first thing to the power times the second thing to the power. The reason I do that is that later on in life, we want to do something where we end up canceling a lot of things, and it's like really, really clear what cancels if every individual base has its own exponent instead of having a product to an exponent. I recommend it. I'm not going to like force you to do it. I mean, I kind of will force you to do it, so do it. But you know, it's equivalent, so it's not like you're wrong. I just would prefer you be more right. Now we're going to multiply everything by x squared. So what's going to happen is all of our exponents for x are just going to increase by 2. So like here we'll get 2 to the x cubed minus 2 cubed x to the 5th, because it's x cubed times x squared, and then plus 2 to the 5th x to the 7th, because it's x to the 5th, times x squared, add the exponents, and keep going. I don't know if you, I never know, like, do you need me to explain that to you? Probably not, but I've definitely learned some things in my life where like I was so confused that literally any useful thing that someone who like knew what they were doing said would have been useful to me. And so I kind of like to talk my way through these as if that's happening. I don't know. So here I got to do 2n plus 1 plus 2, because it's x to the 2n plus 1 times x squared. You add the exponent. So I'm going to end up with 2n plus 3. And then all over the quantity 2n plus 1 factorial. So hopefully I use an approximate. I did. Look at me. All right. So now let's do the last 2 of these. Well, then you might notice that like this problem is related to this problem, right? I mean, if this is f of x, then the limit we're being asked about is just what's the limit as x approaches 0 of f of x, right? And then same thing's going to be here. If this is f of x, This question is just what's the limit as x approaches 0 of f of x. So this, I'm giving you a preview of something that you really do this with series. You don't really do it with polynomials, but because the pattern works out so well, you'll be able to see exactly what's happening. But first, we got to build our series. So I'm going to start with cosine. And this one might actually have some extra steps. Also, I said the word series again. I was supposed to say polynomial, and there's apparently nothing I can do about it. All right, cosine of x is approximately, nailed it. All right, so cosine is even, so it's all the evens. Oh, but we're doing x. Oh, it's just cosine of x. So yeah, let's just dive in with that. I was going to change that into a u and then do a substitution, but like I'm going to make it u and then substitute x equals u. U equals x, I guess, is what I'd really be substituting. Whatever, no one cares. Let's keep going. Plus dot 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 plus -1 to the n. And then we got just x to the 2n because it's even, and then the quantity 2n factorial. Then we're stopping because we're doing polynomial. All right, here's the deal. We're going to do 1 minus this. So it's 1 minus, and then cosine of x. So what that is that's going to be, I'm using like the wrong color here, and then it's going to annoy me in the long run, but what are you going to do? So it's 1 minus the quantity, everything we just wrote. So I'm actually just going to copy and paste so as not to take 600 years. So it's 1 minus that. All right, so what does that mean? Well, there's only one that we're subtracting. So what's going to happen is this one, you're going to subtract 1. You're going to do 1 minus 1. That's 0. Then you're going to take this negative and distribute it across every term. So the sign of everything changes. So we could say that 1 minus the cosine of x is approximately, the sign of everything changes and the 1 disappears. So it's going to be positive x squared over 2 factorial minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. And this is some classic annoying Taylor polynomial stuff, right? So the question says, write 4 non-zero terms. So what do? You go in, you write 4 non-zero terms. Then you have to do some sort of algebraic thing to the polynomial that you wrote, which knocks out one of your terms. So to get your final answer to have 4 non-zero terms, we actually needed 5 to begin with. I needed another term up here to make sure that when I like took one out, I would still have 4. So I'm just going to put it in because the pattern's pretty easy to recognize, I think. It's going to be minus x to the 8th over 8 factorial. Classic. That's going to, if you're in AP calculus, if you're in Calc BC, that's going to happen to you on the AP exam. It's like virtually guaranteed. All right, so what are we doing here? Oh, okay, so we changed the sign though, right? So, okay, so we start off with -1 to the n, but now it's minus -1 to the n. That's like having -1. So what we're dealing with is -1 times -1 to the n. So that's -1 to the first times -1 to the n is -1 to the n plus 1. So actually, down here, I need plus 1. And then it's still just x to the 2n over the quantity 2n factorial. And now I'm really out of room. Because what I need to do is I need to do 1 minus cosine of x divided by x. So like my final step here is I need to divide by x. I don't know if there's a way to salvage the space on this, so I'm just going to go for it. 1 minus cosine of x divided by x. Now what's interesting is everything up here has an x. Since everything up there has an x, all I need to do is knock 1 off the exponent of all the x's. So like I'm going to end up with x over 2 factorial, and then minus x cubed over 4 factorial, plus x to the 5th over 6 factorial. So it's like we're always the exponent is 1 less than the factorial. And it's still, it's still alternating. So we didn't lose that. Then what happens here? So -1 doesn't have any x's. X to the 2n, if you knock off 1, it's just -1. X to the 2n minus 1, I should say. and then the denominator doesn't change. So we get this. Okay, so how does this help us do the limit that's immediately below it? Well, if you look at it, the limit as x approaches 0 of 1 minus cosine of x over x. So let's say we could go forever, right? You have to kind of believe that that would work. Like if 1 minus cosine x over x is approximately the polynomial that we wrote, if we wrote more terms of our polynomial, it would be more that. It would be even closer to that, right? Because as you write more terms, you get more and more accurate. So if we could go to infinity, it would be exactly the same. So what I'm going to do is I'm going to replace 1 minus cosine of x over x with this. Just replace the whole thing with that. So should I just copy and paste that to like save myself a lot of time? That's what I'm doing. Right now I'm lassoing that whole polynomial. Now, oh, and then I lost it. Crud. It's like, it's so hard to, because they're really close to each other. I gotta like make sure I don't accidentally do the wrong thing. Here we go. So this, if I went to infinity, it would definitely be exactly equal. But just look what happens, right? Every single term has an x. So if I put in 0 for x, I just get 0. And that's actually the answer. You could like L'Hopital's this thing, right? Because when you try to plug in 0, you get 1 minus 1, which is 0 over 0. So then the derivative of the top is positive sign. The derivative of the bottom is 1. So you get the sign of 0, which is 0. So this is a way that we're going to be using these things, is we'll write a series, a polynomial. Series is an infinite polynomial. We'll write a series, we'll replace the function with the series, and then just use the series. And it turns out in a lot of cases, it's easier, which is kind of weird. Because I don't know if I would have guessed that when I first started doing things with series. I don't know if I remember series, like learning it. I have like a notebook that I found like a long time ago that has just notes that I had taken on series. So like I definitely at some point sat in a classroom and learned them. But then when I became a teacher and they were like, you're going to teach this, I suddenly, whoa, what happened? I might go back and watch the video. Like, how did this happen? Where did all these dots come from? They're like everywhere. Which I like sometimes think means it's time to wrap it up for the day. But anyway, I found a notebook that like seemed to indicate that I'd learned it, but I would swear I'd never seen any of this before. I don't know how I managed to forget all of it. Equal signs, man. Jeez. It's like a drop 1,000. If this had been a quiz, I'm dropping 1,000 points because of just not writing equal signs. No, because I am writing them. Sine of x divided by x. So this is actually a really common one that you'll find yourself writing a lot. Everything here has an x in it. So when I divide every term, every individual term gets divided by x. Just drop the exponent by 1. So you have x over x is 1. Then you'll get x squared over 3 factorial. One of the keys when you're trying to identify what, so you have the polynomial and you're trying to identify what function it came from, the factorial in the denominator is so crucial to that process. And the reason, if you go back to the top of the page where we memorize things, they all have different factorials in their denominators. Like, do you see every factorial? It's probably e. Do you see only the odd factorials? Probably sine. Do you only see the evens? It's cosine. Are there no factorials? It's probably 1 over 1 minus x. So that's actually like a really important observation that I probably should have made a long time ago in the notes. No, don't write anything because we're knocking one off. 2n plus 1 factorial. Now this question is basically the same as the last one. So I'm going to replace sine of x over x with this polynomial that I just made, and I'm going to do it by copying and pasting. Trying to keep this short. I know I'm saying that when I'm probably at like let me just guess. I don't run a timer. I'm going to guess that I'm at like, I don't know, 14:45. I'll never really know how I did because I'm definitely not going to check, but 14:45 is my guess. Is that where I am? I don't really know. All right, so if I let x be 0, this has no x, so it's just going to stay 1. Everything else has an x, so I'm just going to end up with 1, because it's 1 minus 0 plus 0 minus 0. zeros all the way, right? So we just get 1. And this is another thing. You might have this one memorized because that's like when you first learn them, you memorize this one. Or you could use L'Hopital's on it, whatever you want. Either any of those ways, you're going to get 1. So that's a little application. It's kind of the first application that we really have other than approximating functions. So this is a really important page. Make sure you memorize everything. Know that you can build the polynomial. You start with the base, do your compositions, then multiply by whatever you need to. You'll end up with the answer. And make sure that you remember that you can always just check them on your calculator. Like, play around with that a lot. I think it's the best way to learn is like have your calculator. You know your calculator is not going to lead you astray, and then you just kind of like do the problems. So I'll see you in the next video where we're going to do some more stuff. So see you there.